Solutions by substitutions. To recap, we've covered first order ordinary linear differential equations, where first we saw the first term by itself. This was just a simple integration. And then we saw the first and the zeroth term. This was a linear equation. We also saw separable variables, where in addition to the function of x, we multiplied by a function of y. And we could see y is called separable because the x and y's could separate in the function. Next, we saw first order autonomous, where we removed the function of x and we had it in terms of function of y by itself. After that, we explored exact equation, where the differential was in the form m dx plus n dy equals 0, and the idea was that if the partial of m with respect to y equaled the partial of n with respect to x, we would say that this differential was exact. And the insight as to why we did this is that it led to a solution as a function of x and y set to a constant c. And in the case where it wasn't exact, we could multiply an integrating factor mu on each side, and it would make it exact under two assumptions, where first the integrating factor would have to be in terms of y, and this could only happen if this term was in terms of y. And if that failed, then the integrating factor would have to be in terms of x, as long as this term was in terms of x. But now we shift our discussion to the topic of this video, solutions by substitutions. Our first scenario for this topic will be homogeneous equations, where if we have the following, we say it is a homogeneous function of degree alpha, where precisely what we're saying that if we could replace x and y times a multiple t, then if that t were to come out raised to some degree alpha outside of the function, we would say that it is a homogeneous function of degree alpha. For example, if we had a function x to the 4th plus y to the 4th, we could say that it is homogeneous of degree 4, because here, replacing x and y with some multiple times t, a t to the 4th comes out of the function. So it is of degree 4. Now, how does this apply to differential equations? Take the differential m dx plus n dy equal to 0. Now, as long as m and n are homogeneous functions of the same degree alpha, meaning the following are true, then we could say that our differential could reduce to a separable variable in the following form. Now, how will this work? For a moment, let's say that our assumptions are true. Now, let's let t equal to 1 over x. Plugging t into m, we get the following. And then into n, we get the following as well. Multiplying the x to the alpha over for both m and n, we get these. And if we let u equals y over x, m of xy now equals x to the alpha times m of essentially just of u. And then n of x and y equals x of alpha times n in terms of u. Plugging this into our differential, we get, seeing that the x to the alpha cancel, and if we realize that y equals u times x since u equals y over x, using the product rule, dy would equals u dx plus x du. Plugging in for dy, we now have the following, after doing some algebraic manipulation. Now we see that this is reduced to a separable variable just by the simple substitution t equals 1 over x, where we have one part in terms of x and we have another part in terms of u. Now, we don't have to do t equals 1 over x. We could even do t equals 1 over y, and an analogous procedure would ensue, leading to a similar separable solution. I won't go ahead and work through that. I'll let you sort of work through that. Take a moment and pause and see if you could figure it out. Well, did you? Well, this is how it should look. And now the two parts of the solution are in terms of just y, and in terms of another variable, just v. And this is separable. Now, how do we summarize this whole procedure? Well, step 1, in order for it to be homogeneous, it has to be of the form m dx plus n dy equals 0. And further, m and n have to be of the same degree alpha, as shown. Step 2, we substitute either u equals y over x or v equals x over y, whichever makes the equation simpler. In the former case, we will simplify our differential to this, and in the latter case, we simplify our differential to this. Now, step 3, if we started with u, we would realize that y would equals u times x, and dy would become u dx plus x du by the product rule, and we could substitute for dy. And similarly, if we started with v, we'd get this, and by the product rule, we'd get this for dx, and we could substitute for dx. And step 4, after substituting, we could simplify into a separable form. So in the case of starting with u, we get the following, where our separable would be in terms of just x and u. And in the case of starting with v, we get the following, where the separable would be in terms of y and v. And then last but not least, step 5, we will solve the separable variables. Now, one important thing to realize is that in all this, the idea isn't to memorize these formulas. It's to instead go through these steps and to work your way through it, such that you would end up in solutions like this. Let's take an example. X minus y dx plus x plus y dy equals 0. Step 1, we want to check if it is homogeneous. Now, very first, we want to check, is it of the following form, m dx plus n dy equals 0? Indeed, it is, because we recognize our m, x minus y, and we recognize our n, x plus y. Next, we want to see if m and n are homogeneous, meaning if m equals this equality, and for n, if this equality holds. So, we proceed. We plug in for m, we get tx minus ty equals t to the 1 times x minus y, and then we plug in for n. We get tx plus ty equals t to the 1 x plus y. In either case, we can see that a t to the 1 comes out. So in our case, alpha equals 1, and this is a homogeneous differential to a degree alpha. Now step 2 is we want to substitute for either u equals y over x or v equals x over y, whichever makes the equation simpler. In our case, we will go ahead and try for u. Okay? And when we do that, we realize that y equals u times x. Plugging in, we get the following. Now step 3 is if we started with u, we substitute for dy, and if we started with v, we substitute for dx. But we picked u, so we substitute for dy. Now, dy, by using the product rule, becomes u dx plus x du. Plugging that in for dy, our differential expands to the following. And now we want to simplify into separable form for step 4. Now, keep in mind that when we were going over the theory, we came up with the formula. But like I mentioned, the idea isn't to just plug and chug into that formula. The idea is to work through this whole process to get to that. So that is what we'll do here. So we expand it out. Essentially what we did here, if you notice, is we foiled this using algebra. So that became this, these last 4 terms. And then we distribute the dx. So that became this, the first 2 terms. Next, we separate the terms in front of the dx and the terms in front of the du. So precisely, we have all the terms in front of the dx over here and all the terms in front of the du over here. We see that minus ux plus ux cancel. And then we write the following. Here, the x factored out, and here, the x squared factored out. We subtract the term in front of the du over. We divide the 1 plus u over and then the x squared over. And then we see that we have the x's on one side and we have the u on one side. We have successfully separated our separable. The x in the numerator and the degree 2 in the denominator cancel. And now we have the following. Now that we are in our separable variable form, we go ahead and solve it. So, rewriting it up here. Next, we want to integrate. Upon integrating, we get the following. We separate the integral over the sum. Now, let's go ahead and solve for the second integral first. It should be simpler. So let v equals 1 plus u squared. Doing this, we see that dv equals 2u du, and then u du equals dv over 2. Now, we can plug in for 1 plus u squared, and we can also plug in for u du. Doing so, we can see that the integral rewrites to 1 over 2v dv. And then plugging that in, and then solving for the second integral, we have the following. The 1/2 natural log of 1 plus u squared. Now this integral, how do we solve it? Now this will be quite the process, so let's take a moment and do it on the side. So we bring our integral here. We start with a circle. Now Any point on a circle at an angle theta draws a right triangle, where we have the x side, we have the y side, and then we have the hypotenuse, which is the radius r. And from this, we get the equation of a circle. If we divide the r over, precisely it becomes this. Now we know that x over r and y over r are sine theta and cosine theta respectively, so we get sine squared theta plus cosine squared theta equals 1. This was a trig identity. But instead of dividing by r, let's say if instead we divided by x, then we would actually get this. Now we can see that y over x and r over x are tangent and secant respectively. So we get another trig identity, 1 plus tangent squared theta equals secant squared theta. Here we can see that the 1 plus u squared in the denominator looks a lot like this trig identity. So you can kind of see where we're going with this. Precisely, we'll let u equals tangent theta and du equals secant squared theta d theta. And now if we plug in for u and if we plug in for du, our integral becomes this. But now we can substitute for our trig identity, 1 plus tangent squared theta. And then we get this. The secant squares, thetas cancel out. And then we just have, upon integrating, theta. Okay? But we want to substitute back in for u, because the integral is in terms of u. So if u equals tangent theta, then theta equals arctangent, or the inverse tangent of u. Going back, we plug in our result, and then we plug back in for u, and we get the following. Well, actually, we did a couple more steps. We took the 1/2, and using the log property, we brought it over to raise it to a power, so that's how we got the square root. Adding the natural log over, so we have the constant by itself, and then combining these two natural logs by using the sum natural log property, we should get the following. And this here is our solution. We want to analyze this, so let's clean the slate. If we rearrange our differential to have dy dx equals y minus x over y plus x, right away we can see that y plus x is in the denominator, so it cannot equal 0. In other words, y cannot equal negative x. And this right here is what we call a singular curve, meaning wherever the solution crosses this curve, it cannot exist. To visualize this, we generate our slope field. Right away, you can see that it is a cyclone-looking pattern. Now, why is that, you may say so? Well, to see that, for a moment, let's say our derivative was equal to just the numerator, y minus x. Then, for the region where y is greater than x, this region, we can say that the numerator is positive. But for the region where y is less than x, this region, the numerator actually becomes negative. But on the line y equals x, the numerator becomes 0, well, because y minus x here is 0. Similarly, if you switch it up, letting dy dx equal to the denominator, y plus x, we see that in the region y is greater than negative x, the denominator is positive, and in the region y is less than negative x, the denominator is negative. But on the line y equals negative x, the denominator is 0, because, well, here y plus x becomes 0. Now, bringing the numerator and denominator together, where now we have 4 regions, and the combined effect of all the properties that we discussed, without dwelling too much into the detail, where here we can say that the field starts going to the right, then down. Here it starts going down, then left, left, then up, and finally up, then right. The beauty in this is that one could start from this pattern, the cyclone, and understanding the details of the properties we discussed, they could come up with this differential to define it. Isn't that cool? Anyways, bringing our solution into the mix, setting our constant to -5 and slowly increasing it to 5, we can see a spiral growing out. And this is how it sort of fits onto the slope field. Now, let's not forget about our singular curve. It is essentially y equals -x. So anywhere where the solution crosses this curve, it cannot exist. Now, I want to make a remark on the differential mdx plus ndy equals 0. By now, we've seen quite a ways to go about solving this. First, we ask, could it be separable? Meaning, if the m and the n could reduce to just single variables, then it could become separable. If not, could it be exact? Does it meet this criteria? If not, could it be made exact? Could we solve for these terms and get this integrating factor in terms of x? Or could we solve for this term and get the integrating factor in terms of y? And plugging that integrating factor, we should be able to make it exact. If that doesn't work, could we try homogeneous? In order for that, these equalities would have to hold. And all this, depending on the information you're working with, you can start with any of these options. Anyways, let's move on to our next topic, Bernoulli's equation. Let's bring back our linear equation, dy dx plus p of x times y equals f of x. If we were to multiply y to the n power, this would be a Bernoulli's equation. Now, in the case where n would equal 0, this would reduce to the following, and it would just be a linear equation. In the case where n equals 1, it will reduce to the following, where now it is a separable variable. But for the cases that n is greater than 1, if we let a substitution variable u equals y to the 1 minus n, then ideally we could reduce this to a linear equation. And that is a method to solving a Bernoulli equation. So to illustrate this, let's go through an example. Let's take the following, and then first let's divide the x's over, and right away we can see that in our form it is a Bernoulli equation because the p of x equals f of x equals 1 over x, and then we can recognize that n equals -2. Then our u becomes y cubed, du becomes 3y squared dy. Dividing the 3 over, we get du over 3 equals y squared dy. Multiplying y squared on each side, we get the following. Now we can plug in for the y cubed, which becomes u, and then we can plug in for y squared dy, which becomes du over 3. And then multiplying 3 on each side, we get the following. And now we see that it is a linear equation. We have successfully reduced it. So we can do the procedure for linear equations where first we want to multiply by integrating factor mu. And then upon doing that, we can see that the left side looks like a product rule. So in order to undo it, we have to make it into the product rule. So we recognize that our mu prime has to be mu times 3 over x. Where now, let's solve this. Rewriting it as d mu over dx equals 3 mu over x. Solving this, this would become mu equals cx over cube. And now plugging mu back in and undoing our product, we have the following. Now we can integrate, and dividing the mu over, we get this. We plug back in for mu, the cx to the cube. The c's cancel. And then upon integrating, we get x cubed. And then further, the x cubed cancel out. And then we are left with u equals 1 plus c x to the negative cube. We plug back in for u, and we get this. We multiply x cubed, and then dividing the x cubed over and factoring it out, we have this. And this right here is our solution. And that is how you solve a Bernoulli equation. Now we move on to our next topic, which is reduction to separable variables. Let's say we have a differential of the following form, where it is a function of ax plus by plus c. If we let u equal ax plus by plus c, then we can say that this differential can reduce to a separable variable. To demonstrate this, let's go through an example. Let's try dy over dx equal tangent squared of 2x plus 2y. Now first, is it of the following form? Indeed it is, because we can see that 2x plus 2y is our ax plus by plus c. If we let u equal 2x plus 2y, then du over dx becomes 2 dx over dx plus 2 dy over dx. The dx is cancelled. And then this becomes this. Isolating for dy over dx, we get this. Now, if we plug in for dy over dx into our original differential, and we also plug in u for 2x plus 2y, we get this. If we add the 1 over, we get this. Now we are successfully in the form of a separable variable, where upon separating, getting the u on one side and getting the x on the other, we have this. Recall that earlier in this video, tangent squared of u plus 1 looked a lot like that trig identity where it was equal to secant squared of u. So we plug that in, and 1 over secant is essentially a cosine. So we get cosine squared u du equals 2 dx. Now, cosine squared in itself can't be integrated, so we have to change it into a form that it can be integrated. So this will involve trig identities. Now we can go ahead and just look up identities and just see whatever works, but I want to take this as a moment to work through the trigonometry behind all this. So let's take a right triangle. We have our angle theta, and we say that the hypotenuse is 1. Now, x over r is cosine theta, so x equals r cosine theta. Similarly, y over r equals sine theta, so y equals r sine theta. Since r equals 1, we see that our x is cosine theta on our triangle, and our y side is sine theta on our triangle. Now, let's attach a mirror of this triangle adjacent to it, so it has the same angle theta and the same sides. And now let's add its third right triangle, where the hypotenuse is at the base of the original two triangles, and it has the same angle theta. Now, if this angle is theta, and this angle is theta, and they're on the same line, that implies that this line and this line is parallel. But since these two lines are parallel, and this line is at a right angle to this line, that means this line is also at a right angle to this line. Now, how do we solve for the legs of this triangle? Well, one way to think about it is like this. If we take a look at this triangle, we kind of saw that the x side is always a cosine theta times the hypotenuse, and the y side is always sine theta times the hypotenuse. One way to think about this is that the r, or the hypotenuse, is kind of like a scale on it. So, in essence, that the x side is cosine theta times some scale r star. And similarly, the y side is sine theta times the same scale r star, where the r star is the hypotenuse of this giant triangle. But that is equal to cosine theta plus cosine theta, so it becomes 2 cosine theta. Substituting in for the r star, we get 2 cosine theta times cosine theta, or 2 cosine squared theta for the x side, and we get 2 cosine theta sine theta for the y side. Now let's draw a third line perpendicular to our parallels, and this generates a third triangle, where now we can see that the angle at this point of the triangle is the sum of theta plus theta, so it's 2 theta. Seeing that, we get cosine 2 theta on the x side and sine 2 theta on the y side. Again, there's no scale because the hypotenuse is 1. And now we can see that the hypotenuse of this triangle, 1, plus the x leg of this triangle, cosine 2 theta, is equal to the x leg of this blue triangle, this giant side. So we have the equality, cosine 2 theta plus 1 equals 2 cosine squared theta. And we can rewrite it as such, and this is what we call our cosine double angle property. We just derived it. Now in our case, we are interested in cosine squared theta, so we isolate for that, and we can see that this is an identity that we can plug in. But before we plug in, is it of a form that is integrable? Yes, it is, because you can integrate cosine 2 theta. So now plugging in, going back, we have the following. Separating across the sum, we get this, and now we can integrate. Then upon integrating, we have the following. If we plug it back in for u, we cancel out the 2's, and we distribute the 2 inside the sign, we get this. We subtract the x over, and then we subtract the x once more, so we have the constant by itself, and this right here is our solution.